All right, good morning. Today we're going to talk about 7.2, properties and translations of exponential functions. I'm going to break this up into two sections. The first section we're going to talk about the translations. The second section we're going to talk about the function e, or y equals e to the x. So let's start with our translation portion. Now remember when we did translations before, we talked about several different things. One of those things we talked about had to do with how the numbers affected our function. So, 1, the number that affects x means right or left. We also talked about the number that affects y, or actually affects the whole function. We'll make the function move either up or I'll make it move down. Also, that number we put in front of the function, we usually refer to it as the letter a. That is our stretch or our compress. Does anybody remember the difference? Remember that a stretch is when a is greater than 1, and a compress is when a is between 0 and 1. And one more. If the function is negative, so if we have a negative function, what did that do to our whole graph? It flipped it upside down. Now we did this with several different things already. We talked about it with quadratics, we did it with absolute value, and we did it with cubics. So let's just kind of review some of those we've done before. All right, so we have a quadratic, and we know it's a quadratic because we have a squared term in here. Remember, a quadratic makes a parabola. Let's talk about what the translation is here. We have y equals 3. 3 is a stretch. That's the coefficient or the number in front. That stretches our parabola, makes it kind of skinnier. The x minus 2, now we talked about how whatever's in with x, you set equal to 0, and then solve. So this tells us that, because it's x minus 2, this is 2 to the right. And of course, this plus 7 at the end, this is that whole function goes up 7. Let's try one more. How about this one? Y equals negative 1/2 the absolute value of x plus 1 plus 3. The negative is a flip. So this now has a V that opens down. The 1/2, of course, is a compress. So now this is a flatter V opening down. The x plus 1 tells us this goes to the left. 1 and plus 3 means up 3. So how about let's apply this to an exponential function. All right, so we have an exponential function. Now the other day we talked about how the basic exponential function is y equals a b to the x. We can already see this a here, which we said was our y-intercept, that takes that curve and either stretches it or compresses it. All right, the b told us whether it was a growth or decay. Now up here where the x is, now what was the letter we used anytime we were affecting x? That was our h. That h is going to tell us whether we're going right or left. And then at the end of this function, we always put plus k. And again, that plus k tells us if we're going up or down. So let's try an example. All right, so here's our first example. We're going to describe the translation and then state the parent function or where this started at. So we talked about how this 3 in front is our stretch of 3. Now in an exponential function, we also said this is our y-intercept. This is where it's going to cross the y-axis at 0, 3. However, this right here is going to be impacted if this function moves right or left or up or down. Here we have our base of 2, which means this is a gross, but we have in our exponent x plus 1. This is telling us, if we set that equal to 0, that this whole function is going to move to the left 1. And at the end, here's our k. This is going to tell us we're going to go down 4. So now let's go back and look at this point we have here. Originally, this would have crossed through 0, 3. However, if we're going to move to the left 1 and down 4, our new point this would cross through, if I go to the left 1, that's going to be negative 1. And if I go down 4, 3 minus 4 is also going to be negative 1. So it should cross through the new point, negative 1, negative 1. Our parent function then, where did this start at? Without this translation of left 1, and without this translation of down 4, and without this stretch, where would we want to start at? This started at y equals two to the x. All right, for our second example today, we want to write a function for the translation. So here's our function we're given, y equals 4 to the x minus 2. And they're asking you to rewrite this function with a stretch of 7. Well, where does the 7 go? So when we have a stretch of 7, that's our a value that sits in front. So all it's asking you to do is say y equals our stretch of 7, so 7 comes first. Our base of 4, we're going to put inside a parenthesis, okay, put a dot to represent it, they're multiplied. We're going to raise this to the x minus 2. And again, you can put parentheses around your exponent as well, or it's not totally necessary. Okay, this is something we've done many times. We haven't done them with exponential functions, but we talked about them again with quadratics and cubics and the absolute value functions, where we've taken and changed one function into another. How about we're ready for the second part of today? Let's talk about the function y equals e to the x. All right, y equals e to the x. It is an exponential function, and it's an exponential function because, as we talked about before, there's an x in the exponent. If you were to graph this, this is a growth. E is a set number that's growing, and it's a little more than 2. If you were to put it in your graphing calculator, again, it's an exponential function that's constantly increasing. The second part of this is similar to, let's say, the number pi, except that this has different points at each data spot. So you can see that E is a set value. Now you can translate E, we can find E, but at each of these values, E is a set point. So let's calculate some of those. To find E in your calculator, let's start there. Find E. All right, so as I was saying, you can find the E on your calculator. It's on the left-hand side. It's on what we call the ln, or this is called natural log button. You have to use the second button and then the natural log button. You'll see right above that there's a little, typically in blue, an E to the X. So let's try an example using this. All right, on problems 8 through 10 in your homework today, you're going to have to evaluate. And if we're evaluating, let's say e to the fourth, you're going to just plug this into your calculator. And I'm going to ask you to round to the fourth decimal, to 4 decimal places. All right, so if you plug in e to the fourth, you get 54.59815. And of course it continues. Again, like pi, it just keeps going. E is irrational. If I ask you to round to the fourth decimal place, this is the fourth decimal place. And so if you look to the right, this would take that number up. So if I have 54.5982 if I round. Now, there is another word I want to bring up to you. It's called truncate. Truncate means you just cut it off. If you truncate it, this would just simply be cut off after the fourth decimal place. So 5981. I'm going to ask you today to round, but in the future the word truncate might come up. So why is e to the x important? All right, so let's check out the answer to that question. Why is e to the x important? Well, we use e to the x for interest or exponential functions that are compounded continuously. This is going to be the key word. Anytime you see this word continuously, we're going to use e to the x. Now, if we're talking about compound functions or compounded continuously, we use what we call a PERT. A equals P E and our exponents to the RT. Similar to what we did just the other day where we had compound interest, this one's compounded continuously, which means you're always building off of every single day. Now, P, of course, is your starting amount. The R, as we talked about before, is your rate as a decimal. And of course, T is the number of times it happens. Let's try an example. All right, let's try this example. In this one, we are going to calculate something that's compounded continuously. If you're given the principal of $200, your rate at 4%, and your time for 5 years. We're going to use a PERT. So we have A equals P, which is our starting amount, 200. E is a set, since it says continuously in the problem. R, our rate in this case is 4%. So how do we write 4% as a decimal? That's 0.04. Remember, you're moving it over 2 places to the left. And we're going to times that by the number of years this is growing continuously, which is 5. Typing that into your calculator, you find that in 5 years your account will have $244.28. How about if we try applying it to a real-life situation? All right, so let's talk about this. We have Frank makes $1,400 a paycheck. He deposits half, or $700, to start. If the account is compounded continuously at 5% for 10 years, how much will Frank have in his account? Now, this word continuously means that we're going to use PERT. All right, so we have A equals, again, P represents the starting amount. Now, he's only depositing half of his paycheck, so we're starting with $700. E, are, the rate in this case is this 5%. 5% is a decimal, is 0.05. And he is doing it or leaving this account for 10 years. So 10 is our T, or our time. Now, if we calculate this or type this into our calculator, we find out that he will have $1,154. And, of course, this is money, 10 cents, after his 10 years. So that money has grown quite a bit over those 10 years. The last problem on your homework today is very similar to this. Follow the steps, and you've got this good. If you have any questions, let me know.